Rathod sir.
Yeah, access rights I have given to Saraswati.
Okay, sir, done, not a problem. We have our colleague Kedarnath also here meeting.
Acha, he was there in the morning also. I saw him.
He'll be putting her. So can we go ahead and start the session? Shall we
Oh,
wait for a while?
I don't know. Wait for 3 4 minutes. I have just put a
No,
message on the WhatsApp group.
no problem. Problem.
Just 2 3 minutes. Then let the people do it.
It's okay, sir.
Okay, go ahead, sir. We'll start.
Okay, sir, fine then. So hope I'm audible and clear.
Yeah, you are audible. So just make sure you complete up to 4 o'clock.
Yes, sir. Yes, sure.
If anything is pending now, then you will have to take, you can take it tomorrow morning. Okay.
Yeah, sure, sir. We'll do that.
Okay. Okay.
Mostly I will finish it off, sir. No problem.
Yeah.
Okay, so let's continue the session, everyone. Uh, Before I start, just a quick recap of what we have discussed till now. So, in the beginning, we have seen what is analog flow, the full flow, and you have also seen the demo associated with it on attaching a library, schematic capture, functional simulation, and then drawing a layout and DRC LVS, which is physical verification. Then you have also seen post, sorry, parasitic extraction, post layout simulation, and the GDS creation. So all of this went on with the full custom IC design flow. Now, based on the sub designs that you have generated in the full custom IC design flow, you will convert them into libraries, namely liberties and left files, where liberty files contain all the information and the signal switching information, whereas left files contain all the physical dimensions. Now, both of these lib and left are created through a process called library characterization, and that is how you get the functional and physical information of the sub designs in our nlog flow um, into text form, and these are directly used in these are directly used into semi-custom. Now, why we are primarily using semi-custom flow? Because the design complexity is high, and we cannot handle any design more than let's say 25 to 30 transistors to get it fabricated within 3 or 6. So as an alternative, we go with semi-custom design flow, also called ASIC flow, where where we build application specific designs. So the first step is realizing a specification. So you you declare what exactly is that you need at the chip level, and then you break it down into smaller blocks, and this and generate a micro architecture, nothing but the architecture of the sub blocks. And based on the specifications and architecture of these sub blocks, you start with your ASIC design flow. So first, you write a RTL code defining the functionality. Then you also write a test bench with a series of inputs under which the design has to be tested. And then you go for a functional simulation where through instantiation, all the test bench inputs are forced onto your main module, and the values are returned, which is what you see either in the waveform or on the console numericals. And then you come to synthesis. Uh, sorry, functional simulation is done in 3 stages: compilation, elaboration, simulation. Once that is done, you come to synthesis. You have 3 inputs, and this is again a 3-stage system. So your inputs are your RTL code and your Liberty file, which are mandatory. And you'll also have your SDC file, which depending on your design can be mandatory or optional. But it is very strongly recommended to have one. And once you give all these three, your synthesis is done in 3 stages: translation, mapping, and optimization. Under translation, high level code is converted to machine level language. Under mapping, every instruction or block in your code is mapped with the designs in your Liberty file, same functionality. And your SDC acts as a filter between mapping and conversion. So once mapping is done, in order to reduce your cell count, optimization is done as a part of synthesis where your redundant logic is removed out. And after that, we have looked at certain guidelines like not using to avoid nonsensible constructs, and properly reading in your input files, properly redirecting your output files, because all the names are case sensitive, and etc. All that stuff. So once you're done with synthesis, as I said, you'll get your block level SDC, gate level netlist, and timing area power reports. Now here the thing is your area and power are direct reports. That means you'll get a direct numerical estimate that this is how much is being dissipated or consumed. But when it comes to timing, that is not the case. When you perform timing analysis, actually checking whether every bit of data, when your design is active and running, every bit of data being transferred from one point to another point effectively and safely or not. The thing is, when you're handling a large design, a very complex design, there is a pretty good chance of at least a bit of data missing. So what happens is the place where you're expecting zero, sorry, the place where you're expecting one, you might actually have a logic zero, which makes the whole design give wrong outputs and collapse your functionality. So for that reason, we go for timing analysis. So where exactly do you use this timing analysis in the ASIC design flow? The answer is at multiple locations. Once you do your synthesis, you you once you do your synthesis, you go for timing analysis, and this time before it is because it is before the physical implementation, it is called pre-layout ST, pre-layout timing analysis. So once you start your physical design, that means from placement, floor plan placement, and routing, etc. At that point, it's called post-layout STA. That means you are dealing with layouts, and then in the presence of those physical aspects, you are checking your timing. That is post-layout STA. But just after synthesis, you don't have any physical aspects yet in place. So that's why it's called pre-layout timing analysis. So the same is depicted here in the picture. Next. So when I say timing analysis, there are basically two types: dynamic timing analysis and static timing analysis. Dynamic timing analysis means you intend to check both the functionality and the timing. That means for a given combination of input, is the data being transferred from point A to B in time or not without being lost? So you check that for every input combination. So let's say you have a AND gate. You have four different combinations: 0, 0, 0, 1, 1, 0, and 1, 1, right? So you perform timing analysis for all the four combinations and also check whether you're getting the expected output or not. So to keep it simple, DTA is like simulative timing analysis. Check the function as well as your timing. Okay. Uh, Whereas when you come to static timing analysis, you're not concerned about the functionality. You're not seeing what for a given input what is the output you're getting. That's not of the concern. You only check whether when you force an input, is it being propagated without being lost or not, especially when you have sequential cells. Sequential cells are those gates or are those designs which work on a control signal. That control signal could be a clock or enable signal or an okay. So basically for timing analysis, we prefer registers. Uh, Basically, we prefer registers. So let me talk in terms of flip-flops. So if you take a flip-flop, it runs on clock. So um, o- uh, so a flip-flop is captures an incoming data only at the positive or negative triggering edge. That means your data has to be sent carefully, or it must be propagating in such a way that does not come after the trigger edge arrives. It should come on or before the trigger edge of the flip-flop so that it is captured properly. Now, when you talk about combinational cells, there is no such issue because any moment, whenever the input arrives, accordingly your output is generated, right? So in STA or DTA, this timing part is common, but in DTA, you will also be checking the functionality. So let us just have an overview of what is what. Now, under DTA, dynamic timing analysis, is basically used to simulate transistor level circuits or using SPICE model. Next slide. So as it deals with both functionality as well as time, uh, one benefit is that it gives you a complete picture. Gives you a complete picture of the state of your design, whether it's being in line with your expectation or not. But the problem here is, as your design complexity increases, the number of components you use also increase. That means your timing analysis also gets complex. So we need accurate and uh, proper timing models for each and every gate or device that is present in the design. Next. And another drawback is that higher the number of inputs, the combinations which are to be checked also increases exponentially. So if you have, let's say, one or two inputs, you will be checking two or four combinations. But as you can see on the screen, if you have 100 inputs, you will have to check for 2 power 100 combinations, and that is a number that you see now. So with the complexity increasing day by day, you cannot. I mean, it's not practical to check for functionality and timing for such a huge number of combinations. Next. So that is the reason we prefer static timing analysis. The functionality is being checked for any complex design. The functionality is anyway being checked under the front end. So now, if you check your back end and make sure that the logic uh, after the logic of the gate level circuit you have and your RTL code is the same. So you can, when you split it into two steps like this, one for timing and one for logic check, you can, it is still a go ahead, right? So that is where after synthesis you perform logic equivalence check, and the same continues even at physical design. Okay. Anyway, coming back, so for STA, which stands for static timing analysis, does not check your functionality. It by default assume that the functionality is correct. So it will only consider for a given data, just one bit of data. It could be anything. Is the propagation being proper, or are there any violations? Next. That is what it checks. So in this process, when you compare your DTA and what happens is DTA is more of a vector based approach. So that means, so the more, if you want more accuracy, you will have to add more vectors. But as I said, it becomes difficult if you have more number of inputs. Whereas when you come to STA, there could be something called false paths. So, false paths are nothing but your false alarms. There will be nothing there, but you will have to respond to it. So here false paths are almost the same. There won't be any data flow, but they physically exist. So your tool has to address them also. So they are called your false paths. So as a designer, as an engineer, if you uh, if you find any of these false paths, you will be actually mentioning them in your SDC file. If you recollect it, you also have a constraint called set false path, wherein you can declare that. So if you remove that false path, only then your timing analysis will be more efficient, and every path, every single path is checked the timing. So just a simple comparison between DTA and when you look at the advantages, DTA is very accurate but time taking. Whereas STA is fast, exhaustive, but it does include your functionality. And DTA is suitable for small designs, but not for complex and large designs. Whereas STA can be used for large designs as well. But the only thing is, as the design complexity increases, you will have to make sure you define the timing exceptions or just false paths. Okay. And one more drawback for STA is that it becomes difficult in handling asynchronous, purely asynchronous design. Okay. Next. So, with all that justification, we generally prefer static timing analysis to be done. And coming to the functionality, as I earlier, the first step of checking your functionality is your simulation, and then your logic equivalence check. Okay. So there is, just for your information, there is something called formal verification, where the RTL code you have written is checked for its coverage. Whether is there any unnecessary lines of code that does not serve the purpose, or is there any part of your code that is not really adding to the efficiency of your code. So all that is checked under formal verification. But the logic equivalence check, LEC, is done only after your okay, after your synthesis and during or after P and R, placement and route. Is not but your physical design. Okay. I think that answers the question of Dr. YNM, sir. Sorry, the initials. Saraswati, just go one slide back. So that is about formal verification and LEC. Sting to STA, as I said, there are two types, pre-layout and post-layout STA. When you talk about pre-layout STA, you actually take in only the gate level netlist, which is an output of synthesis, then your timing library, nothing but your liberty file.lib, and your timing constraints in the form of SDC. So you take these three, perform your timing analysis, and generate your timing reports and log files. But if you are dealing with post layout STA, then along with the three inputs, netlist, liberty file, and SDC, you also add the delay that is extracted from your layout. Okay, it's very similar to the parasitic extraction and post layout simulation in your full custom IC design. Next slide. So in STA, once you make your design entry and verification, just after synthesis, you perform pre-layout STA, and then once you start your physical design, you you also perform post-layout STA. In your pre-layout STA, you primarily check for timing in an ideal case, assuming no parasitics or no extra delays apart from the internal delay of a device. Whereas when you go to PD, you will be taking in extra factors such as the parasitics, internal delay, wire delay, etc. Next. So these factors like the parasitic information, etc., are taken into your STA in the form of two files, SPEF and SDF. SPEF, SPEF stands for Standard Parasitic Exchange Format, which is created from your physical design, and SDF is Standard Delay Format, contains the delay values of each cell. Okay, so this depends on both your liberty file as well as your parasitics. And SDC is what you already know, right? So you first load your design and then read in your SDC, SPEF, and SDF, and then check your timing. For every path, what is the delay, propagation delay experienced by a bit of data. So in any path, if your data is being lost, or if it is not reaching its destination within time, that is reported as a violation. So this is the SDC I was talking about. This is your block level SDC. Okay. So as I told you, block level SDC very specific to your design. The input SDC for synthesis is chip level. Here it is block level. So you can see that every constraint is applied for every individual pin or every individual block. So that is why you see multiple constraints repeating for uh, different pins and different ports. Okay, so this is how your block level SDC looks like. Next. So as I earlier told you, you can see under extensions there is something called set false path and set multi-cycle path, set max delay. These are only a few which are used to improve the efficiency of your timing analysis. So when you're creating, you will have to keep both your synthesis as well as timing analysis in mind and create it accordingly. Okay, next. So once you're ready with all your inputs and you perform timing analysis, so what exactly is happening during a timing analysis when it runs? What are the factors or what are the concepts that are being involved? I'll take you through a quick overview. What is what? I request everyone to pay close attention for the next 5-10 minutes. So when you actually take a design and well, let me take a simple AND or NAND gate itself. You have two inputs and one output. So that is the only cell in my design. Assume. So when I start my timing analysis, I first have to look at the delay. When I give my inputs A and B, the output is being generated at the output pin Y. So the output is not immediate, and the output is not instantaneously generated the moment I give my input. There is a certain delay in between. So that delay between your input and output is called your cell delay. Okay. Now when you further dig in at your input or at your output, there will be switching of values from 0 to 1 or 1 to 0. Now even these switching of 0 to 1 or 1 to 0 ideally does not happen instantaneously. So for that there is something called slew or transition time. So this is the time taken by a signal to switch between 0 to 1 or 1 to 0, be it at the input or output. So at the output, because this signal is being, if this signal is being given as input to the next gate, that means your first cell has to push the output so hard that it goes as an input into the second signal. So whatever capacitance that the second cell offers, that will become the load for the first one. So that is how your transition time is affected and causes a certain delay. And the third one is wire delay, which is due to the parasitics. Next. So all these three delays are considered during your, while calculating your propagation delay. Okay. So Um, so to help you understand it better, here let's assume each delay being represented by a arc, by a arrow. Okay, so the arc that represents a cell delay is shown in blue, and we named it as cell delay arc. And that wire delay is shown as net delay arc. And the delay that is induced because of control signals like clock, enable, set, reset, etc. Sorry, clock or enable, etc. are your constraint arc. Okay, so let me just help you out. So here, if you take a simple AND gate, a two input AND gate, you have two inputs, A and B. So there is one arc from input A to output Y, and another arc from input B to output Y. So that means these two are two different paths where cell delay comes into picture. Okay, arcs are just a representation to show you the path how the data propagates. If I give only input A and do not give input B, your output is not properly formed, right? So only from the instant I give an input B, your both the inputs are taken, multiplied, and then your output is given. So, so, so that is how your cell delay arcs are taken. And wires, higher the wire length, higher will be the resistance, because resistance is rho L by A, right? Resistivity into length by area of cross section. So higher the length, higher is the resistance. That means higher is the delay. So if all the wires are shown with red ink, the net delay arc. The third one is constraint arc, and as I said, constraint is nothing but a condition or a regulation that is put onto your design. So here what happens is, for a combinational cell, you do not have any such conditions for them to operate. The moment you get your inputs, your output is generated with a slight delay. But when you talk about sequential cells, something like a D flip-flop, your data actually moves in or moves out depending on your clock trigger. That means here, only when you have your clock trigger, your input is being read from at the pin D. And after a certain cell delay, the same uh, data is being sent out through Q. So that means here, when you check the propagation delay of D flip-flop, it is first all the wire delay till D or clock plus the constraint arc delay from clock to D. And once the data is read from clock to Q, it is only based on clock, your output also will be sent out, right? That's why here the cell delay arc is from clock to Q and not D to Q. Okay, for D flip flop, D to Q arc is not be present. So wire delays, external wire delays plus constraint arc delay plus clock to Q cell delay. All of these delays cumulatively will give you the time taken for a bit of data to pass through the top one. So that is how your all your propagation delay is calculated. Is this clear till this point? Any questions? Next slide. Next. Any questions from it? Okay, fine. So when we talk about signals like clock or enable, we have seen how the constraint arcs comes into picture. But if we are talking about asynchronous, it's like set, reset, or clear, the same concept is applied, but with a slight difference. Here, for asynchronous, we take recovery and removal timing arcs. That means now, all these spins are not dependent on any control signals like clock or enable, etc. Right? So the time or the instant from the instant of your active clock edge, if you got the positive clock edge, then the difference in instance between your asynchronous signal going low to the active clock edge, that time is called your recovery time, because once your asynchronous pins like reset goes low, that means your design is getting back to work. And it and if you have an active clock or a sequential cell that works on your clock, the time between this asynchronous signal going low and the active clock is your recovery time. So your design will recover itself and get back. Okay, but if what if we reverse the case? What if the active clock edge first comes first and then a reset signal is enabled? That case, where until the time reset is high, everything stays at zero. But the moment that goes down, the moment reset goes down to zero, the time difference between the or the latest clock edge till the reset, the point where reset goes down, that is your removal time where all your data stored till then are removed. So that is your recovery time and removal. Very similar setup and hold that we shall talk about the next slide. Next. So all these propagation delays are actually calculated across four types of timing paths. So the first one is register to register, edge to edge. Second one is input to register to output, and input to output. So as you can see in the colored arcs from your input side on the leftmost to the output on the rightmost. First, let's go with path 4. Path 4 is input to output. That means from your input port to your output port, all the paths that contain purely combinational logic. The paths where you have only purely combinational logic or merely wires or input to output uh, type timing path. Okay. Now, if you if you have at least one sequential cell in between your input to output port, then we split it down into two different timing paths. From your input port till the input of the flip flop is one path. That is your input to register. And then the output of your register till the design output pin is your register to output port. Input to output is purely combinational. If there is at least one sequential cell in between, input to register and then register to output. Now, if you have more than one sequential cell, then input to register will be one path, and then the output of first register to input of second register will be one path, which is reg to reg path, and then the second flip flop output to your design output will be the input path. This way, your design may contain any number of paths out of all these four categories. Okay, your design after synthesis may contain at the gate level may contain any number of timing paths in any number across each category. Okay, so your input to output path starts and ends with the ports, design ports, and then your input to register starts with the input port and ends with the D pin of a flip flop. Okay. Um, Whereas a register to output port input but does not start at Q. Rather, it starts at clock. Why are we starting it at clock? Because of our delay arc. Our delay arc for a flip flop starts with clock, goes to Q. That is why the delay path starts with the clock of second flip flop and ends at the output. And when you talk about reg to reg, it's just a combination. Starts at clock of first flip flop, ends at D pin of second flip flop. Okay, I hope there's no confusion here. Next. So next. Next slide, Saraswati. So when you particularly talk about any path involving at least one sequential cell, be it input to register, register to register, or register to out. In any of these, the inclusion of this flip-flop actually invites two timing concepts, setup and hold. Anyone who is completely unaware of setup time and hold time from the audience? Yes, please let me know in the chat. Are you comfortable with setup and hold time, or do you want me to explain that?
No, no, I think these basics everybody knows. This.
Are you sure, sir?
Setup,
I mean, the application
I
point
think
of view.
people know about setup time, hold time. Don't worry. Go ahead.
Okay, sir, fine then. So, so just a quick review. So setup time is the maximum time window before a positive edge of clock or whatever is the trigger edge. The maximum time window before the arrival of the edge for the flip flop to get itself ready to capture the incoming data. That is your setup time. So your total clock time period minus this setup time. That means let's say your total time period is 2 nanoseconds and your setup time is 100 picoseconds or zero point 0.1 nanoseconds. So that means 2 minus 0.1. 1.9 nanoseconds is the time your data has to move from whatever starting point till and reach the deep corresponding flip-flop. If your data reaches on or before 1.9 nanoseconds, then well and good, no problem. You 1 nanosecond setup time, so your flip-flop switches from off to on and comfortably captures the data. Okay, so out of this required 1.9 nanoseconds, suppose your data is reaching at 1.5. That means it has an extra 0.4 nanosecond extra time. Apart from setup time window, your data has an extra 400 picoseconds or 0.4 nanoseconds time. So that extra time is called setup slack. And now when you just mirror this, what do you call, when you just mirror this phenomena uh, at your trigger clock edge, you will get your hold time. So the minimum time your captured data must be held stable before it is sent out again is your hold time. So your complete clock time period minus your hold time is uh, is your required time. So let's say your data must be held stable for at least the same zero point 0.1 nanosecond. That means after the clock edge, your data must be launched only at uh, only from t is equal to 0.1 nanosecond till t is equal to 2 nanoseconds. In case if it is launched before this zero point 0.1, because it is not held stable, it will not be propagated properly, which could lead to loss of data. So that is your setup time and hold time. Next. So this is a example of your pre-layout timing analysis. So we'll discuss this along with a tool. Next slide. So as I earlier said, for your so that is your timing analysis, how every path is calculated with and checked whether your data is being reached within the time or not. So if you consider the pre-layout stage, you'll be taking only netlist, timing library, and constraints in SBC. So and perform STA. But when it comes to post layout, along with these three inputs, you'll also add your SPEF and SDI. Next. So just to summarize the inputs and the flow for your timing path, you will have to, in order to perform timing analysis, be it by the tool or on your own, you will have to first understand or determine what are all the timing paths available in your gate level circuit. Okay. So you will have to go through each one of them and classify them into any one of the four types: put to output, put to reg, reg to out, or reg to reg. Okay. So once you are done with it, now you will have to check whether is it a purely combinational cell, purely combinational design. Do you have sequential? If you have sequential, do you want to do setup or hold? So then, based on your setup or hold, you will have to calculate the propagating delay from your input across all the timing paths possible based on the arcs and calculate the arrival time. Required time can directly be taken from clock time period minus minus the setup time or the hold time, what is, and minus uncertainty. That way you calculate the slack. So in case at any point that means your data is being the timing violation. Else, if it is zero or positive, please do remember that as I said earlier, we generally check it for the worst case and the best case, right? So next slide. So for setup, we always check it the worst case, and for hold slack, we check it in the best. Why? If you recollect it back, slow library, maximum delay or maximum time, and worst. That is how we stitched it up. So here the setup is a maximum time window. So that means in the worst case you have to check for the worst. Whereas when you go for hold, it's a minimum time window. So you see for a quick moving. Okay. So the tool you use for timing analysis is Cadence Tempus. So this is just a screenshot of how your design is loaded and then calculated. So to the left side, you can see the menu where you have options for reading ST, SPEF, and SDF, the primary inputs of your timing right, and course also provides you a user-friendly debugging window where you can check the timing reports every individual part. Next slide, Saraswati. This snap. I hope the concept. Any questions in this point before we move to? So any questions till this point from anyone? Go to the next slides. Okay, I believe everything is clear till this point. I hope everything is clear with everyone till this point. So let's continue with the tool demo. So we'll quickly go simulation, synthesis, and the timing analysis. Saraswati, over to you.
Oh, thank you, Sai Krishna. Let me continue with the tool flow demo. Good afternoon, everyone. Here onwards, I will be continuing with the tool flow demo. For today's, as per the today's agenda, we will be going with the synthesis flow as well as pre-layout timing analysis. So before start up with the synthesis and pre-layout timing analysis, let us give us some glimpse about the functional simulation, how we can start up with the functional simulation using the graphical user interface. So already in the previous session, you might have been gone in detail for a functional simulation, how to write a Verilog code and even with a test bench, and how to simulate all these things with a command line. So I'll be just in today's agenda we will be discussing in detail about the synthesis and timing analysis. So I'll be continuing further. So let us see the functional simulation with using the Cadence Innovus simulator. So as you can see here, I'll be just opening the simulation tool. Before start up with the simulation tool, I'll be sourcing my CHS cell script, and even I'm sourcing the CHSRC file where all my tool parts will be mentioned and even license path will be mentioned. So SSH is my Linux script where I will be invoking Linux commands. It will help me to invoke the Linux command. So to start up with the functional simulation, I'll be using NC launch space -u. As you have already known, so NC launch is my graphical user interface, the tool which will be used in the graphical user interface mode. If I am directly using a command line, then directly I can go with the NC Verilog, NC simulation, and NC elaboration. So currently I'll be just showing with the graphical user mode. So I'll be using with the NC launch. So as you can see, NC launch is the tool name, and even directly I am using -new ampersand. So -new ampersand which will indicate like previous, for example, for this first time, the design, like any designer, first for any design, first time I am invoking NC launch or a simulation tool. So at that time, I'll be using -new. So on subsequent calls, directly I can use NC launch ampersand. So this is the first time I'm doing the simulation using the graphical mode, graphical user interface mode. So I'll be using NC launch space -new. So currently I have already invoked the tool, simulation tool. Based on the simulation tool, I'll be getting my NC launch window will be open. From the NC launch window, I'll be using the steps. As you can see, multiple steps, single steps, options were there. So if you want to do, if you are going for the multiple step, in the multiple step options, we can able to see compilation, elaboration, and the simulation in detail. So directly, if I'm going with a single step, directly I'll be taking you to the simulation. So here in this case, I'll be taking you with the simulation, multiple steps. So I'll be checking with the multiple step. As you can see, once I am checking with a multiple step, to start up with a compilation, to start up with the NC Verilog compilation part, so we need to create a CDS lib. So where my work lib directory will be created. So I'm just selecting the create a cds.lib file. So once after creating the cds.lib file with the current directory, you need to make sure that whatever the path your directory of the path you are setting, that should be proper. So sometimes it may changes. So you need to be taken care. So I have already given the file name cds.lib. I'm just saving the cds.lib file. Once after saving that cds.lib file, currently I'm doing this functional simulation without using any libraries. So that's why I'm just choosing don't include any library. Once after I'm selecting don't include any library, I'll be taking the functional simulations without using any library. So now I have already created my CDS file for a worklib directory. So I'm just selecting OK to come out. So now I have already able to see the graphical user interface of NCC simulator, that is NC launch window, as you can able to see. So here already I have a as in the directory you can able to see my CDS .v file for a FIFO. Currently I am using a FIFO design. So as you can see, .v file, that is nothing but my RTL code for a FIFO design. Like in the for regarding the codes and all, I am not taking much because in today's agenda we will be going with the synthesis part in detail. So here I am just telling the main parts of the code. Currently, we were writing the code with a module and in what and all the inputs we were using and what and all the output ports I am declaring. Based on that, what is my logic, that will be explained with the behavioral code, because I need to proceed further with the synthesis process. Where synthesis process, we need a synthesizable code. So usually for any other abstraction levels or as for example structural level we have, and even data flow modelings we have, different levels of writing RTL code we have. So usually those things might not be synthesizable. So that's why we were here in the for a FIFO design we have written a code in a behavioral modeling. As you can see, this is my behavioral modeling code. So this is my RTL code. The same way this even you can able to see the for the functional simulation to check the waveform. I'm forcing my inputs in the test bench. So using this test bench, we will be able to see the simulation waveform. So I'm just again coming back to the simulation window, that is NC launch graphical user interface. From here we have a three panels. As you can see at the left hand side, you can able to see the file browser where I will be able to see my input files, which and all I am using for compiling and elaborating and simulating the codes. So this is my file browser, and even you can see the command entry window. This is a command entry window where you can able to see if any errors I am getting with respect to my code. that can be shown here. So once if I am running the code, you can able to see here. If you are getting any errors in the code, then it will be indicated in the red color. So now you can see one more right hand panel where you can able to see the work directory, as I have already told. Once if you are creating the cds.lib file, so my work directory will be created in libs. So these are the things which we can able to see with the, and even this is also called as a design area. So where we will be checking with the compilation, elaboration and simulation parts in this design. So even we have a file options for the toolbar menu where we can set up my inputs here also. So currently I am doing with a graphical user interface. You can able to see my input files, that is a FIFO.v and the testbench.v. So whenever I am compiling or elaborating or simulating, each and every stage I need to select the files which I am compiling or which I am elaborating. So currently I will be starting up with the .v file compilation. At the top of the toolbar menu, you can able to see the toolbar menu. You can able to see the elaboration for compiling the design. We have a compilator tool. So as I am showing you, this is a Verilog compilator. The next is a VHDL compilator. If I am returning the code in the VHDL, then you can able to use the VHDL compilator. So currently I have written a code in a Verilog, so I will be using Verilog compilator. So I am just pressing the Verilog compilator, just select on the Verilog compilator, and it will compile the design. As you can see, once after for the compilation process, I will be using the Verilog compilator. Once after compiling the design, you can able to see in the command entry window where it will be showing. If I am getting any error with respect to the code, that will be shown here. Currently, it is in a blue color, as you can able to see. So I am not getting any errors in that particular code. So if I am getting any code, that will be shown with a red color indication. So now I have compiled with the .v, that is a RTL code. Next I want to compile my test bench. So I am just selecting the test bench from the left side panel of the NC launch window, and I am selecting on. I am just directly launching the Verilog compiler. So I am just clicking on the Verilog compiler. You can able to see I am able to compile the test bench also. Once after compiling, you can able to see once if you are extending this work lib directory, from the work lib directory you can able to see my test for a .v file, what is my top model, that will be shown here. So even for a test bench also, it will be shown with the top module of test bench. So now once after compiling, the next process is elaborating the design. So how I can elaborate the design means, again I am coming back to the right panel of the NC launch window, where I will be selecting again with the top module of RTL and the top module of this test bench for elaborating design. So currently I have selected the top module of RTL and elaborating the design. As you can see, the elaborator for elaboration process, I will be using the NC lab. NC elaborator is my tool which is taken from the NCC simulator. I'm just clicking on the elaboration. You can able to see I'm getting elaborated with the design. The same way, even you can elaborate test bench as well. So select the test bench from the right hand panel from the work lib directory and elaborate the design using the launch elaborate option available from the toolbar menu. So once after elaborating, if any further violations with respect to with respect to elaborating process, if I have any errors in the code again, that will be shown in the command window, console window, where I can able to see the errors. Based on that error, again I will be going back to the codes and we were modifying the code, and again coming back to the compilation and simulation, compilation and then elaborating and simulating the design. So till now I have already checked with the elaboration process. I have elaborated both top module of RTL and the test bench. Now again I am extending with a snapshot. As you can see from the snapshot, I need to check the simulation waveform. So to check the simulation waveform, I'll be selecting my test bench. From the snapshot, you can able to see the workclip dot FIFO buffer test bench module. So I'm just selecting this test bench test bench snapshot from the snapshot directory, and I will directly use the NC-Sim tool for a simulation process. For a functional simulation, I'll be using NC Simulator. So I'm just clicking on the NC Simulator. As you can see, even the command prompt window, I'm not getting any error. I'm proceeding further. So once after compiling the design and after elaborating the design, I'll be checking with the simulation. Once if I check with the simulation, then my simulation window will start to pop up. So just wait for a minute to open the tool, simulation tool. As you can see, in the simulation process, we have got a two. One is a design browser window, as you can see, and another one is a console simulation window. So design browser window, where in the left hand side I can able to see my test bench waveform, test bench I am able to see. So to check out the waveforms, I'll be directly taking this test bench to the waveform window. So as you can see, so usually I need to right click with the test bench, and then you can just select the send to waveform window. Once after selecting the send to waveform window, it will take me to the waveform window where I can check with my simulation outputs with whatever the inputs I have given in the test bench. So with respect to that, I will be able to see simulation output. And one more window, as I have already told, that is a consolation simulation window. Usually, that consolation simulation window, which will be used for setting up my input variables. If I am even we can able to see the output, as well as even you can set up my inputs in that consolation window, and based on that you can able to verify the output. So currently I am just selecting the test bench from my design browser window and taking that into a send it to waveform window. Once after selecting the waveform window, it will take me to the simulation waveform where I can able to see my simulation. So till now, till I have not yet able to see the simulation. Once if I select the run option from the waveform window, I'll be able to see my functional simulation with for the FIFO design. As you can see, this is waveform. So as a FIFO stands for first in first out. Based on the inputs I have given in this test bench, based on that I will be getting my outputs. As you can see, if you want to minimize and see the complete design, you can just zoom in and zoom out for a better understanding. So as you can see, I am just zooming in. So zooming out, you can do. By doing that, you can able to see complete output waveforms. As you can see, whatever the inputs I am giving with the test bench, based on that test inputs, I am getting the data outputs. So this is how we were checking the functional simulation. I will not be taking detail because mainly we will be concentrated with the synthesis process and timing analysis. I'll be just showing you the graphical user interface with the functional simulation. This is how we were doing the functional simulation using the Cadence Innovus simulator with a compilation, elaboration, and simulation with separate in the multiple stages. Using multiple steps, we were doing the functional simulation. This is all nothing but the functional simulation of the RTL codec test bench. So till this point, is there any queries? If you have any queries, you can just put it in the chat box. We will be addressing. If no doubt means, I will be proceeding further with the synthesis. So shall I continue?
Continue.
Okay, fine. So, okay, let me give me a minute. I'm just closing these things. If I'm going a little bit fast, means you can just let me know. So feel free to interrupt so that I'll get to know whether you guys were sync up with me or not. now we have already checked with the functional simulation. Now let us see with the synthesis. Before start off with the synthesis, so what is the command used for synthesis processes? That is a Genus. I'll be just taking the same way. I'll be giving the CSH, which is a shell script command, and again I'm sourcing the CHSRC file for loading the tool paths as well as the licensing, and I'm using a command Genus. So for a Genus tool, by default we will not be having a graphical user interface. We need to give a command for checking the graphical user interface. I'm just giving a command Genus for a synthesis. So let us give us some time to open the tool. Till that time, I'll be just checking you. As previously we have already, as my colleague has been already explained with what are the inputs required for the synthesis process. As you can see, RTL is one of the primary input, and the timing library, and even with a constraint, and even with the left file. So usually left file is optional, only it will be considered when we were doing with the physical synthesis. Currently I am going with the logical synthesis, so it is an optional file. Even if you are giving also, it is not a problem. So if you are not giving also, it won't make any difference. Only when we were concerned about the physical synthesis part, then we will be must and should we need to give the we need to use a physical library, that is a left file, as one of the primary input at that time. So as you can see, RTL code, it is already, I have already told, for a synthesis process we need to write a code in such a way that it should be synthesizable code. So you need to write a code in a behavioral modeling so that it will be a synthesizable. So most of the time, sometimes if you are using data flow or any structural modeling, in that case you might end up with some non-synthesizable constructors which are not which will not allow you to synthesize the gate level netlist. You should need to take care with whatever the codes you are using for the synthesis process. It should be always a synthesizable construct to generate the gate level netlist. So let us see the timing library. As I have already in the presentation part, as it has been, always has been explained. Like we have mainly three cases. Currently, I am using the 90 nanometer technology for this tool flow demo. So as you can see, I will be having the three cases where I will be having my timing library. One is slow.lib, fast.lib, and a typical. So if we consider with the real-time in the real-time designs or the real-time applications for the real-time designs, at that time the designer may interested to go with a worst case or best case or all the three, or even with a typical. So usually if the designer interested to perform the design specifications with respect to the worst case, then directly they can go with a slow.lib. If they are interested with the best case, then directly they can go with a fast.lib. If they are with the typical, then directly they can use a typical.glib. That is nothing but the typical.timing libraries. So some of the times the designer were interested to do with all the three cases. In that case, all the three files should be loaded at a time. So currently in this design, in this synthesis process, I'll be using the worst case, that is nothing but the slow.lib. So I'll be loading only slow.lib file. So let us see what is there the slow.lib means. Usually in the slow.lib, that is a timing library file, starting at the starting part, you can able to see the units of all the attributes given in the slow.lib library. So all the input, whatever the units given for the complete attributes, that informations will be at the starting you can able to see. Afterwards, each and every cell's functionality or characterization informations will be given for each and every cells. As you can see, number of cells or number of standard cells. For each and every standard cells, what is my operating, like what is my power consumption, even timing reports, whether transition time or even with a fall time, rise time, all informations will be given for each and every cell. So that is what we were taking here. In between me, I am using this slow.lib, and what are the values which were fetched from this slow.lib, I'll be explaining in the tool part itself. So this is how we can see the slow.lib file. So I'll be just closing this. As you can see, this is my timing library input, and one more input file which we were using, that is a constraint file. So usually constraint file will be for a real-time designs. This file will be given by chip architecture. So because all these things, this file will be created based on the designer specifications, mainly like how much clock frequency they are using, based on the clock frequency, how much the timing period, and what and all the input delay they want to set, or the input transitions they want to set. All these things will be based on the designer specifications they will be setting. So currently, for example, I have created this design constraint file. As you can see, here I have taken the clock period as a 2. Clock period as a 2 is nothing but usually the time period is reciprocal of frequency. If you are checking with the frequency, means 500 megahertz, as you can see. So currently I have taken a clock period with the 2 nanoseconds. As in the tempos or even with the SDC file, you can able to see each and every time if I am mentioning the timing, means the always units should be in nanoseconds. So wherever it is taken, whether it is a clock period or any input values, the timing values should be taken in the nanoseconds. In the tempos tool, as well as even with checking with the constraint file. So mainly the advantage of this constraint file means it will be taken into consideration when we were doing the timing analysis. So as you can see, my clock period is 2 nanoseconds, and I have taken a rise time, fall time with a 0 and 1s. I am setting up these, and based on, for example, this is for 90 nanometer technology I have taken. For this 90 nanometer technology, I am setting the input delay is of 40%. So as you can see, 40% of my clock period. So 40% multiplied with my clock period, that is 2 nanoseconds. That is how I am setting here. So it may changes with respect to the technology nodes what we were using. So if it is a different technology node, then my input delay setting might change. So it all depends on the technology node which we were using. So for example, I am just showing you here. The same way here I have used 10% of my clock period. So I am just setting the input transition with a 10% of 10% with a clock period. As you can see, that is a 0.2. And max capacitance, I'm not still now I have not known anything. So I'll be just setting a random value, that is a default value 30 max capacitance. I'm just setting with the 30. So rise time, fall time, anyway it will be 0.1 by default. So uncertainty, as you can see, one more, that is a clock uncertainty. Usually sometimes we need to set a margin for the clock signals. So sometimes it may vary. So to avoid that, I need to set a clock like margin for the clock signal. So I'm using the clock uncertainty, that is a 0.01 default value I'm just taking. This is how I am giving the SDC constraint for the design. So as you already saw, this is also one of the input file for synthesis. So let us start off with the synthesis. As I have already invoked the tool, as you can see in the root, you can able to see my tool got invoked, and I am able to see. Currently by default I am not able to see any graphical user interface window. So if you want to use a graphical interface window, you can use a command GUI_show, take you to the graphical mode. So you can see this is my synthesis graphical user interface. Till now I have not loaded any design, it is empty. So usually for a synthesis tool, that is Genus tool, we were setting up the inputs in the command terminal itself. So in the prompt window only we will be setting at the starting. Once after setting the inputs from the terminal, then we can able to see the outputs or even log reports, everything from the graphical user interface. Directly from the graphical user interface, we can't able to set the inputs. First, we need to go command by command in the terminal itself. So how we can set the inputs for the synthesis process? Let us, as you have already gone through the process. So actually first we need to set up the timing libraries, and even with the RTL paths, all the file paths should be set, and then I am reading the library file and reading the HDL, that is a Verilog file, then elaborating the design, then reading the constraint file, and then starting up with the synthesis process, that is translation, mapping, and optimization. These are the process we were proceeding further. So how we can start up means, let me zoom in so that it will be visible. If it is not visible, you can just let me know so that I will be zoom in so it will be visible, because these commands and all important. We can because for a synthesis tool we will be setting all the inputs with the terminal itself. So first command what we will be doing is, first we need to set my static whatever the timing libraries I am using. So command used for setting the timing library is setDB. SetDB is a command I am using for setting up my library. So setDB space slash space dot init underscore search. As you can see here, search. I need to set library. So I am using init underscore library search path. As you can see here, it is able to, if you are using the tab from the keyboard, it will show me the switches available with that particular command. It will be helpful for you guys to understand what are the switches available, because when we were typing the command, we might end up with missing the cases, the spelling mistake or case sensitivity or the spacing issues we might create. So if you are using the tab, it will show the switches. Based on the switches, we can able to use the commands properly. So now you can see I am able to use the switch, that is a init underscore path. So I need to give the search path. I am giving, where is my lib file? That path I am giving here. As you can see, this is my lib search path.
Saraswati.
Yes, sir.
Hello.
Yeah, tell me, sir.
No, I'm Kedar. Please be little bit slow. You are hurrying up.
Okay.
Please be bit slow.
Yeah, fine. Okay, if I'm going too fast, if you are not able to understand, please free to interrupt me so that you will be sync up with me. If anything you are not able to understand, you can raise a query so that I will be addressing meanwhile.
Fine. Just be little bit slow, and you can
Okay.
full screen. Full screen you can make it.
Yeah, fine. So is it visible or should I need to make a zoom in little bit?
Yeah, zoom in little bit. Yeah, now it is fine.
Fine. Okay. So the first step is I am setting up the path for my library file. As you can see, so double dot slash indicates I am already in the directory, as you can see, synthesis directory, but I have kept my all the files in the design directory. As you can see, this is my design directory, but I have a synthesis directory. Inside the synthesis directory, I am invoking my tool. So that's why I am using double dot slash in the sense I am going back one directory. So I am using this slow.lib, the lib directory where I kept my slow.lib. So this is how I am setting the library path. So once after setting the library path, again I need to set the very file RTL code path where I have kept my RTL code. That directory path I need to set up. So the command used is setDB space. Again I will be using slash space dot init. Here I have previously I have used lib. Be changing it to HDL because I need to set a path for my RTL code. So I am using HDL. So once after that, again I will be taking double dot slash to getting back to the directory. There I will be keeping my RTL code in the RTL directory. So I am just giving the path. You can see. So this is till now I have set up the path for my timing library and the RTL code. So the next step is I need to read my timing library. Till now I have not yet read any file. I am just setting the paths. So now I need to read the timing file. So how I timing file? What is the command used is set db. Again I am using a set db space slash again space dot library. So which library I am using? As you can see, I have used a tab to check the switches. So you can use that library. Then directly you can mention the file name. So I'm just given the library name. Now in the code you can mention which file you want to read. As I have already told, for this logic synthesis I will be using worst case, that is nothing but slow.lib file. Even if you are using with the best case, then you can just put a flower brace and you can give a path for all the files at a time. For a real-time design and all, if they are going with all the three cases, then they can directly load all the files. So currently I am going with a single, that is a worst case. I am giving slow.lib. As you can see, slow.lib file I have given. So now I have already reading the, as you can see, the timing library got read in the Genus tool. So now I need to, now I have already loaded the timing library. Now I need to read the RTL file. So before reading the RTL file, I need to set my design name. What is my top module name? So the design I need to set. How I can set means I will be using a command set design. So this is the command I will be using. So in the sense, whatever my top module name. So as you can see, for the top module name, whatever for RTL design, what is the top module and name should be given. So as you can see from the RTL code, what is my top module I have given in the code, that will be my design name. So as you can see here, FIFA buffer is my top module name. This name I should need to give. So again I am coming to terminal. As you can see, set to design top module name. So FIFA is my top module name. Up with the top module name. So once after setting up with the top module name, I need to read my Verilog or RTL code. So again I will be using a command read HTL, and I need to give the path. Where is my RTL code file? So previously I have already set it up with a path. So here directly I can read the file. As you can see, FIFO.v is my RTL file. So directly I am giving FIFO. FIFO.v is my RTL file, so I am just giving FIFO.v is my, I am directly reading the FIFO.v file. As you can see, so here are some, based on the code, it will be, based on the code, my Verilog RTL file will be read in the Genus tool. If you are getting any errors, warning means you can ignore. So some you can able to see some of the synthesizer non-synthesizable constructors which can be acceptable. But if you are getting any error, in that case only you can able to go back to the code once, and you need to check whether is there anything non-synthesizable constructors available in the code. Then you need to make sure that is a synthesizable. So if you are not getting any errors means you can proceed further. So currently I am not getting any errors in the code, so I will be proceeding further. If you are getting any warnings means you can ignore, not a problem. So now I have already read with the timing library files, even with the that is RTL file. So all these things I have read. The next step is I need to elaborate the design. Till now what and all I have done, I have set it up with the input files by reading all the things. So now I need to elaborate the design. So what is the command used for the elaborate design is elaborate $design. As you can see, I am using a tab to check the switch. So it will help you to get to know the switches available in the command prompt window. So now I am just entering. So it will elaborate the design. Once after elaborating, next I need to check is there any unresolved or unsolved, any unconnected pins in my RTL code, or any unconnected pin or floating pins available in my code, that I need to check. So before startup, so I am using a command that is a check design. As you can see, check design space hyphen unsolved. So you can see the switch unsolved. If you are having any unconnected pins or floating pins available in the code, that will be shown by using a check design option with a hyphen solve unresolved. So I'm entering. As you can see, there is no unresolved references in the design. So there is no any empty modules in the design. So I can proceed further. So till now I have already read with the timing library and RTL file, that is a RTL code file, and elaborated the design, and I have already checked is there any unconnected pins or any modules which are not which are empty, which are not described in the .p file. All those things we have checked. So next process is I need to read one more input file, that is nothing but the constraint file. So I'll be reading the command used for reading the constraint file is again read SDC. Previously I have used read HDL. Here I will be using read SDC command. So as you can see, read SDC, and I am giving the path. So here I have not set it up the path for a constraints. So directly I need to give the path here. So what is my path where I have kept? Again I am going back one directory. From the one directory back, I'll be having my constraint directory. In that constraint directory, I have kept my constraint file. Is a constraint underscore top.sdc. This is my SDC file where this is the SDC file path where I have kept my SDC file. So once after entering, you can able to see what and all the constraints I am giving in the .sdc file. That should be read properly. See here successful and failed. So if I am not giving proper constraints in the SDC file, so that may leads to fail options. So currently I have given a constraint file properly. So you can able to see all the inputs, input delay, what and all I'm doing, or even clock transition or uncertainty, input delay, output delay, all these informations I'm giving, that is taken properly. If I have not given properly, if I have made any mistakes with the commands or even with the values, that may throw with the failed options. As you can see here, failed options. So if you are getting any failed options here, then you need to go back to the constraint file once again and make the corrections paste properly, and then reload the SDC file once again. Unless the fail options were 0, you should not proceed further with the SDC file. If any one single option is also failed, also the SDC file will not read properly. So it will whatever the SDC file we were taking, that might not read properly. So to avoid that, you just make sure that any failed option should be 0. So as you can see, now I have already read all the 3 input files. That is so these are the 3 input files which we were already set it up, and we have already loaded into the Genus synthesis tool. The next process is to start up with the synthesis process. As previously we have already discussed, that is a translation, mapping, and optimization. So proceed further with these 3 processes. We need to set all the three process or all the 3 stages to a effort level to a medium, high, or low. So it depends, again it depends on the designer's specification, whether designers are intended to give us effort level to medium or high or low. That depends on the designers, whether if they want to for a translation, that is a generic, if they want to do with a high level, then they can set up the effort level to high, or if they want to set with the low, they can set with the low. So here I'll be going all the 3 process with the effort level to medium. So I'm using a command to set up. So the command used is setDB. Again I'll be using a command setDB with the effort level. So I just use a sin underscore. As you can see in the switch, it is showing sin underscore. Here I need to mention the generic. First step is generic, that is nothing but the translation part. So I'll be giving the effort level to medium. So first this translation process I'll be setting up with the medium. The same way I'll be setting remaining 2 process with the mediums. Set DB. Previously I have used generic, now I'll be using map. As you can see, so sin generic, sin map, effort level to medium. So the same way sin opt, effort level to medium. So just now I have set it with generic, I'll be setting with the map, medium again. The same way I'll be setting with the optimization also. STTP synopt effort level to medium. So once I am setting with all the effort level to medium with translation, mapping and optimization. That is nothing but generic, mapping and optimization. So now we will start to check with the translation. So as you can see, generic. So to start all the three process or the three stages, I'll be using the command sim generic. So sim generic in the sense the translation process. So usually what is the translation process means we will my codes to a Boolean expression formation. The conversion of my RTL code to a Boolean expression formation. So here it will be technology independent. So we were not including any technologies. Directly my RTL code will be converted into a Boolean expression. As you can see, once after the translation or generic process completes, next I will be doing sim map. Sim map in the sense whatever the Boolean expression I got, that I will be interfering the two. Then I will be binding those things to the my standards, the technology libraries. As you can see, predefined cells available from the timing library. So that is again I will be using sim map. Sim map process will helps me in the synthesis tool. The tool infers the whatever the Boolean expression generated from the generic process, that will be binded with the technology library available. So with that technology level, the technology library is available, it will be binded and it will generate the proper gate level netlist. So once after completing this, so I need to make sure that whatever the cell size to avoid the area consumption more, so we need to optimize the design. So that can be done by using SIN optimization. So as you can see, SIN optimization is my process. These are the three steps which we were using for the synthesis process. As you can see, synthesis optimization. So synthesis optimization means it will simplify the equation. So whatever the after the mapping process, what is my Boolean expression with the technology dependent, that will be simplified further. So this we are optimizing the process with the synthesis tool. So all the three processes were completed. If you want to see the gate level netlist in the schematic waveform, so then again I am coming back to the graphical user interface here. So I have not yet loaded the design. So it is showing empty, but from the left hand side you can see design browser option. You will be having gate cells in the sense what is my top module name and how many the count of the cells. So how many cells were there in that particular design, that you can able to see. Terms is nothing but whatever the instance, usually the terms indicates the instances or hierarchical instance pins available in the design. The same way net is nothing but again you can tell nets or the H nets. Here you will be taking as a H nets. So standard cells again, these are the predefined cells which are taken from the timing library, that is a slow dotlet. So as you can see, usually these standard cells represent leaf level instances in the design. So leaf level instances in the design will be represented by standard cells. So if I want to open the schematic representation or the schematic structure of the gate level netlist, directly you can select the stop module and go to schematic view module option from the violation browser, or else you can go to the plus option available from the GUI. So directly I am taking from the schematic view. Here also you can able to see. So this is my pictorial representation of my schematic wave, the gate level netlist. So even you can able to open. Yeah, even you can able to press on this plus option available in the graphical user interface mode. We have a different options. The layout, schematic layout only you can able to see while doing the physical synthesis, because there we will be using layout informations. Based on the layout informations, I can able to see the layout structure in the layout option. So directly I can see here the schematic waveform also. So the same way design browser, as you can see at the left hand side, you can able to give the glimpse of the designs. What and all the my top model name, what and all the instances available, standard cells available, net information, all these things we can able to see with the design browser. And one more options we have, that is a HDL viewer. So if you go to HDL viewer, in this HDL viewer, I can able to see my RTL code. So once if we go to directory, the parental directory where I kept my RTL code, you can able to open that RTL code. So I'm just opening, I'm just selected the FIFO design and opening. So you can able to see the RTL code here also. Even you can make a corrections if you are getting any violations with respect to the synthesis part also, you can make the corrections, or you can directly go back to the file and you can able to see. So these options available for the graphical user interface of synthesis tool. Even we have some objective attributes also. The objective attributes is nothing but completely whatever the timing reports, area reports, all these informations we can able to see in one single window. So you can just select any information and click on the calculate option. You can able to see the current. For example, if I want to check with my internal power, you can just click on the calculate option. It will take me to the. I'm just showing you here. As you can see here, I'm just selecting internal powers. I want to calculate this. I'm just clicking on the calculate option. It will give values here. So this is one way of checking the attributes, or else you can go with the options available from the graphical user interface of Genus. As you can see, check design option is also available. Here also we can check. I have already explained this command in the tool itself. So I can just further go with the report files, summary reports of gate level netlist, all these informations we can able to see here. If I am going to the summary report, here you can see whatever the cells, standard cells or the cells available from the timing library mapped in the mapping stage. All these lists will be given here. These are the cells got mapped in the mapping stage with each and every cells, how many instances were available and what is the area and which library it is taking from. All these informations we can able to see with the summary report. So this is this is about the gate level netlist summary report. So the same way, if you want to see any static gate count or even with netlist statistics, also you can go further. So if you want to see netlist statistics means how many sequential logics, like how many sequential circuits or the sequential cells were available or logic cells were available or any inverter buffers were available in my design. All these informations you can able to see with netlist statistics. So these are the informations we can able to see with the graphical user interface. If you want to see all these things in the terminal also, you can generate the report. So even power reports also we can check, even timing report also we can check in the graphical mode. So let us show me one like how we can check any reports in the terminal. So I'll be just taking report underscore. Before going to that, let me write out my netlist and STC file. So what are the command used for writing out the netlist is write underscore HDL. And again I will be using a file name, that is FIFO underscore netlist. But the file extension should be again .v. So FIFO underscore netlist.v. So I am generating this. The same way I will be generating SDC file also. As you can see, write SDC option is also available. So I will be just use a command greater than, and then you can use the file name with whatever the comfortable file name you want to give, you can give it. So I'm just giving random SDC. So always the file extension should be taken care. When you are generating the gate level netlist, you need to give a .v. When if you are writing out the SDC file, you should need to give the file extension should be .sdc. These are the things we should need to take care while writing out the design. So I have already generated netlist and SDC file. So if you want to see back all those things, again I am coming back to the directory. As you can see, this is my gate level netlist and this is my SDC file. So let us open the file gate level netlist. As you can see, this is my gate level netlist file. So usually what netlist, what it contains, all these informations, let us see one by one. So gate level netlist means it contains the informations regarding all the logic connectivity of all the standard cells. If we have any designs in the macro, so currently FIFO design I have taken without macros, so I will not be having any macro informations. If I have taken any design with a macro also, so all the connectivity informations related to the macros, standard cells will be available in my gate level netlist. So, and even if you want to see, and it also provides the details of all the nets and its connectivity. As you can see here, whatever the net connectivity, all these informations I will be able to see. And even what are the instances, what are all the standard cells. Standard cells are nothing but these are the standard cells and the standard cell instances. All these informations will be given in logical standard cell informations will be given in the gate level netlist. So as I have already told, file extension will be always it will be a .a file format. So even give some interconnection details like pin connections, port connections, all these informations will also be given in the gate level netlist. So this gate level netlist will be taken as primary input further for the physical implementation process. So this is all nothing. This is all about the gate level netlist. So now again coming back to the reports, as we have already told, we were generating the reports with respect to power, performance, area. So the timing report, area report, and power report. All these reports can be generated. Two ways we can generate. Directly we can check with the graphical user interface mode, or if you want to generate any reports, then you can directly use a command in the command prompt window. So if you want to generate any power report or timing report, you can just use report underscore timing, or even report underscore gate counts, or report as you can see the switches, it is I just use the tab option, so it is showing what and all the switches available with respect to the reports. So even you can check with the power reports also available, timing report also available. So only the thing is you need to mention the file name greater than symbol I am using this file. What is the file name I am giving? FIFO underscore. If I am checking with the timing, I am just giving the report should be in the RPT file extension. The .rpt file extension I will be giving. So now the timing report has been generated. The same way if you want to generate any gate count, so you can use gate count. So I will be using FIFO gate .rpt. The same way if you want to generate any reports, you can use to report underscore area, report underscore power. And file name you can. So I'm just giving pwr.rpt. Always to generate any report, the file extension should be .rpt. So now you can see all these files will be generated. Report underscore power. Sorry. I want to generate the power report. I'm just using the command report underscore power. So FIFO underscore power dot rpt. So these files will be generated. So again I am coming back to the directory. As you can see, whatever the reports I have generated, all these report files were generated back end. So if you want to see one by one, you can just open up. This will give the count of the gates available in the gate level netlist. So as I have already told, all these things I have already shown in the graphical user interface mode. All these information I can able to see with the gate count report from command prompt window. The same way, if you want to check a power report, I'll be just going with the power report. From the power report, you can able to see leakage power, dynamic power, and the total power. So how much power consumption will be taken for complete design, that will be mentioned here. So total how many instances were there for that particular instances, how much power has been taken. So this is all about the timing reports. Once after invoking the Genus tool, backend we will be the two files will be generated. One is genus.command file and another one is genus.log file. So usually genus.command file is nothing but whatever the commands I am executing in the terminal, the prompt window, that will be listed with a command, genus.command window. So in this file, all the commands, what and all the commands I have executed in the terminal, that will be listed in this file. The same way, and even you can see log file. So log file means whatever the execution summary. So what and all the things I have executed in the terminal with a summary, in detail summary. All these execution summary report we can able to see with the log report. So these are output. Even you can for in detail you can go with the tools different options available here. As you can see, DFT is also there, floor planning options. If you are doing with the physical synthesis, floor plan options we will be using, and if you are going with the low power options, then we will be using different low power options available in the synthesis tool. For the further, only for a logic synthesis I am doing. So I'm just using few main things, the main important things required for this design. So if you want to see in detail, you can just play around the tools to get to know. So due to shortage of time, I can't show everything in the tool itself. So I'll be just showing you the important things what you should need to know in the synthesis process. So this is all nothing but the synthesis part. So now I have already generated the netlist, and I need to further with the timing simulation. As you have already known, so the timing simulation will be done after. Usually, the static timing analysis will be done in a two stages. One is a pre-layout STA, that is a pre-layout static timing analysis. Another one is a post-layout static timing analysis. Pre-layout static timing analysis is nothing but once after generating the gate level netlist from the synthesis process, directly we will be going to the static timing analysis. That is nothing but pre-layout STA. So when it comes to post-layout STA, we will be taking the routed database. From the routed database, we will be using the gate level netlist and additional spec file and STF file as additional inputs, and proceeding further with the static timing analysis. That's why we were calling it as a post-layout static timing analysis. So here, to start up with the static timing analysis, till this synthesis part, is there any doubts regarding this? You just let me know, or we will clear and then proceed further with the timing analysis. So till this point, is there any doubts? So till this point, is there any doubts? Shall I proceed further with the timing analysis?
Proceed, ma'am.
Okay, fine. So now I have already generated my gate level netlist, and even with the STC file. So I'll be just closing this. Just give me a minute. The same way again I am giving a CHS command for shell scripting. Again I will be sourcing the CHSRC file for the tool path and the licensing, and directly here I am using timing analysis. For a timing analysis from the Cadence, we will be using Tempus tool. The Tempus tool, to invoke the Tempus tool, I will be using Tempus command. So once after invoking, let us give me a minute to zoom in so that it will be visible. As you can see, to start up with the timing analysis, pre-layout static timing analysis, So whatever the inputs we were taking that is constraint file again, and whatever the netlist I have generated from the synthesis. So whatever the netlist I have generated from the synthesis, this netlist I am using, and a constraint file, and again the timing library which is available from the foundry. All these three inputs I am using for starting up with the pre-layout static timing analysis. And one thing you should need to take care, so pre-layout timing analysis in the sense we were using till now we were using ideal clock signal. We have not used any propagated clock signal. So that's why we need to take care in the pre-layout timing analysis. We will be checking with respect to the timing violations with respect to setup check. So even if we are getting any old timing violations also, we will not be bothered, because till now we have not used any propagated clock signal. So that's why we will be checking only with respect to the setup timing analysis. Come back to the constraint file and even synthesis optimization process to fixing the timing violations. So this is how we were doing. This is how we were going with the pre-layout static timing analysis. So once up here for a Tempest tool, by default I'll be getting my graphical user interface, as you can see. So once if we start up with the timing analysis, here also I will be setting my, first I need to read the input files. What are the input files I am using, that I should need to read here. So here I don't have any layout information, because still I am in a synthesis stage. So once if we go to post the routing stage after the PD implementation, in the PD implementation stage, then we can proceed further with the post layout static timing analysis. See what and all the inputs, as I have already told. One is a gate level netlist, another one is a timing constraints, SDC constraints, and the timing library. These are the main input files I'll be using. Just give me a minute to open the tool. Okay. So this is my graphical user interface of Tempest tool, Tempest timing sign-off solution tool. So from the Cadence, this is also industry standard tool, as you can see. So currently it is empty because I have not yet started to load any design. So let me start up. To start up with the tool process, usually sometimes what happens, I am running with a different technology nodes for a different designs. So tool will be taking by default any technology node. For example, previous design, if I the 45 nanometer technology or some other nanometer technology, then the tool will be taking that the previous nanometer technology by default. To avoid that issue, so what I should need to make sure is that, like, whatever the technology node I am using, that technology node should I need to mention. So what is the command I am using for to mention the technology node is the set. Again I will be using set design, set underscore design underscore mode hyphen process. So process in the sense which technology node I am using. So currently I am using 90. I will be giving 90. So what happens if I am not giving this technology node, the process technology node? So it will be taking by default. If it is, if even though if I am running with a 90 nanometer technology, if I have run with some other technology, that technology node will be taking. To avoid that, I will be setting up the technology library once again. So once after setting this, the starting input files, usually for input file setup, we have an option from the file option. You can able to see read design and all the input files we can read. So currently for a pre-layout STA, I need to read my SDC file. So read design option will be able only if I have any physical database. So currently I don't have, only gate level netlist is there, and I am not using any spec file SDF file because I am doing pre-layout STA. So these two files only used when I am doing with the post layout STA. So that's why I will be setting up the command using, I need to read my gate level netlist using the command. So I'm just coming back to the terminal. So first I need to set up my timing library. If I have a physical data, directly I can load the physical data. Once if I am loading the physical data, I'll be able to load my gate level netlist, timing library, MMMC file, that is a view definition file, all these things. So that will I'll be showing you in the later stage when we were going with the post layout static timing analysis. This is just a pre-layout static timing analysis. I'll be just reading directly all the input files through the terminal. So what is the command again for reading the timing, even with RTL gate level netlist and even with a constraint file is? Let us see one by one. So first I want to read my timing library. So as you can see, read underscore lib, and I need to give the path. Where is my library? So I'm just giving, as you can see, double dot slash is going back to the directory once, and I'm giving the lib directory. In that lib, I'll be having slow.lib is my file. So this is the timing library file which I am loading. As you can see, this is my now I am able to load my slow.lib file. The same way, I need to load my gate level netlist. The command used again is read verilog, and I need to path. So as you can see, I have generated the gate level netlist in synthesis directory. So I'll be choosing synthesis directory. So from here, whatever the name I have given, I'll be selecting with that. As you can see, read underscore verilog with the directory path of the file available. Where is my netlist file is available, that path I need to set up for reading. So as I have already told, the gate level file extension always it will be a .v, where V stands for Verilog. So now I have already read the slow.lib, that is a timing library inputs, and gate level input. Now I need to, as I have already told, once after reading the library netlist, I need to set up my top module name. So usually I need to set up my top module name. How I am going to set up? The command used for setting up the top module is again set to top module, and I'll be giving the top module name, that is free for buffer. So this is the command I am using, and I am using again any unconstrained pins. As you can see, sometimes in the gate level netlist, few of the pins will be floating. So unconnected pins will be available, because some of the blocks we might not be used completely. Only few of the pins or the input or output ports will be used. Some of the ports will be left floating. So those things will be ignored by using a hyphen ignore option. So any undefined cells are there in the design, that will be ignored. So I'm just using hyphen ignore undefined cell. So I'm just setting up the top module name, and I am also mentioning any undefined cells were there in my gate level netlist, that will be ignored. So as you can see, now I already read all my gate level netlist timing library. Now next I need to set up my constraint file. So I need to read my constraint file. So again I am using the command read SDC. As you can see, read SDC, and again I have to set up the path. As you can see, constraint and constraint top underscore top dot SDC. So this is how I am setting loading the SDC file. I am setting up the SDC input file for Tempest tool for proceeding further with the pre-layout timing analysis. So now I have already set it up with all the input files. So next I need to check out the timing report. So before checking out the timing report, let us see what is my gate level netlist schematic. As you can see from the schematic, this is my gate level schematic capture, which is once after loading the gate level netlist, I can able to see the schematic captures of the gate level netlist. So this is my schematic capture of gate level netlist, as you can see here. Even we were able to see this in synthesis tool also. So now here the main thing of the Tempest tool is checking the timing reports. So to how to check the timing reports again, I'll be using the command report underscore. Even you can check all these things in the timing debugger window also. I'll be just using the commands here, report underscore timing, and I am using register path. Usually, for a static timing analysis, we will be the entire design will be divided into the time. So, as you can see, a complete design will be divided into the timing paths. Based on the timing paths, if you are getting any violations with respect to setup or hold timing violations will be checked. So, I will be just checking with the register to register path here. I am just using the report underscore timing from all register to all register. And I need to use with respect to setup and with respect to hold. So how I can check means I can use late for a setup and early for hold. So if you are doing setup check, then you can use hyphen late. If you are doing with a hold check, then you can use hyphen early. So that I will be able to generate the timing report. So as you can see, I am getting the timing report. So here you can see the timing report will be showing for only one path. So as you can see, this is my report with respect to setup check. As you can see here, this is my setup check. That is only showing for one path. If you want to see the number of paths, you can just give the number of paths. So let me generate any one timing report, and in detail how we were checking the slacks and all we will discuss. I am just using the same, and also I am just checking the max path. For example, I am just saying max path as 10. It depends on, like, you can just check with the 10, 15. So how many paths were there in this particular design? That many paths you can checking with the. So I'll be using setup .rpt again. The file extension, this is a report again, the file extension will be .rpt. So I'm just entering the .rpt. The same way I want to check for hold violations or hold timing report. Then I'll be using, instead of late, I'll be using early. So the same timing report from all register to all register hyphen early, which will take me to the hold check with the max paths of I'm giving 10 same for hold. So here I'm giving the file name hold.rpt. So I have generated these two reports. Again, I will be coming back to the pre-layout timing pre-layout STA directory. As you can see, hold report and setup report, setup timing report and hold timing reports has been generated. So if you want to see the timing reports in detail, so I will be just going one by one. As I have already told, I have taken a maximum of path 10. You can able to see from 1 to till 10. So you can see able to see till 10. So if you are having any violations in any path, any check type, whether it is with respect to setup or with respect to hold, that will be shown with flag value. If you are having any violations in the setup check or even with a hold check, it will be shown here with a violated setup check. Currently, all the timing paths were met. I am not getting any timing violations with respect to setup check. So it is telling my setup check has been met. So usually, what is the setup check and what is the setup timing and how we were calculating the slack and on what basis we will be telling that like we were the timing path has been I'm not getting any timing violations with respect to setup checks or hold checks. On what basis we were telling all this? Let us see one by one. So if I am taking one example, let me take one example, that is a part 1. From the part 1 you can able to see it is showing the setup check has been met. In the sense, I am not getting any timing violations for that particular part. So even you can able to see usually what is my setup timing. Setup timing is nothing but setup required time minus arrival time. So required actually slack how we were calculating for the setup means we were checking the required time minus arrival time. So again we have how we were calculating arrival time and how we were calculating required time. All these things we can able to see here. Arrival time in the sense whatever the begin point the arrival time and whatever the cell delay values from for each and every cells, what is the delay value I am getting. So these delay values, all these cell delay values will be taken. So the total cell delay value plus begin and arrival time. So this will gives me a arrival time, total arrival time. And how I am getting a required time means, as you can see for a setup check, I'll be using other end arrival time and my phase shift. The phase shift is nothing but again my clock period. So and I am using the setup. This is a setup check I am doing. Setup timing analysis I am doing. So I'll be subtracting the setup value. As we have already told, this value will be taken from my slow.lib. That is a timing library as previously have told. That is slow.lib. From the slow.lib, I'll be taking this value. These are all standard values given in the timing library. So uncertainty, as you can see, uncertainty is also there. This uncertainty value I'll be taking from the constraint file. Using these things, I'll be calculating my required time. Once if I get to know the required time, from the required time minus arrival time, I'll be able to check my slack time for setup check. So this is my slack I am getting for this particular path. So as you can see, the slack is positive. Usually, how we get to know whether the path is violated or any timing violations if I am getting in the particular path or even with a particular design, how we will going to get to know means whenever you are taking any slack in the negative value, if you are getting any negative values, be considering it as the timing path is violated. So currently you can see my slack is so that's why it is not showing any timing violations. Even though if it is still we have a slack, this is not reached to 0. It is not mandatory like always my slack should need to set to 0. It is not mandatory, but always we should need to take care like the slack should be positive. Then only my timing violations will the timing check has been met. If it is any negative values for my slack, whether with respect to setup check or even with respect to hold check. So the slack is negative, then I should need to get to know that timing path is violated. I will be having a timing violations whether with respect to setup check or with respect to hold check. So based on that, I need to fix the timing violations. So how I need to fix the timing violations? Again, as I have already told, in the pre-layout STA, only we will be concerned about only setup check. Even you can check with that hold report also, hold timing report also. The thing is, till now we have not used any propagated clock signal. So we will be, even if we are getting the timing violations with respect to hold check also, we will not be able to fix completely. So only when after routing stage, that is nothing but my post layout timing analysis. At that time, I'll be taking care of hold checks as well as with setup check timing analysis. So here in the pre-layout timing analysis, we will be more concerned about the setup check timing analysis. If I am getting any setup check timing analysis, now you might be getting the doubt. Till now I have saw I am not getting any violations here. So if I am getting any violations with respect to my setup check timing analysis, how I can fix those violations in the pre-layout STA stage means two ways we have. One thing again, I need to come back to my constraint file. As you can see, I have told these constraint files I need to optimize. So I need to optimize this constraint file further, and I need to go to synthesis optimization, incremental optimization process I need to go. So these are the ways how we can fix the timing analysis in the layout STA stage. So only two cases. Yes, yes.
Sorry for the interruption. I think we have spilled over the time. So can you just wrap it up? If there anything else, we can
It's
start it tomorrow.
end of the session only. It's the end of the session only. Anyway, I have already checked the timing report. Anyway, I have already explained. Only the thing is fixing how we were doing, that will be explained. So as you can see, violations, if we are getting any timing violations, again we have to come back to the constraint file, and we have to check with the, we have to optimize the constraints, SDC constraints, and also we have to go to synthesis incremental optimization process. Then we can able to fix the static timing violations in the pre-layout STA. So this is all nothing about the timing analysis. So in the pre-layout STA, how we were fixing all those things with the different stages, we will be explaining in the pre-layout stage in the tomorrow session. So here it will ends up with the timing pre-layout timing analysis. So any further doubt regarding these things till this point? If you have any doubts, you can just put it in the chat box. We will be addressing.
Madam, madam, it's okay. I think if there are any doubts, tomorrow also you are available, no?
Yes, sir. PD part will be continued tomorrow, no? So physical design implementation part.
If anybody has any doubt, we can ask tomorrow morning.
Yeah. If you have any doubt before starting the session, or even chat box also, you can put it. We will be addressing meanwhile.
Okay.
So this is all about the today's agenda regarding synthesis as well as with the power static timing analysis. So anything else, sir?
No, nothing. So thank you, Sai. Sai Krishna, thank you very much for this 3 hour session continuously taking for morning 2 hours and again this 2 hours. Thank you very much. Thank you, Naveen Shankar. I don't know if he's there right now or not, left. Okay. Just say thanks to him. And thank you, Saraswati ma'am.
Most welcome, sir.
Yeah. Your speed by default is very, very fast. Okay, thanks a lot. So looking forward to your tomorrow's session. So tomorrow we will meet again back at 10 o'clock. So exactly same schedule. Okay. So tomorrow also same
Sure,
schedule.
sir.
So thank you.
We hope, yes, sir. We hope today's sessions were useful and up to your expectation.
Yeah. Now participants will only tell, but it was good information. Thank you.
Okay, thank you everyone.
Yeah, thank you, everyone.
Thank you everyone. Thank you very much. And I think Entuple team can leave, but others, I can. If you want, you remain connected. Otherwise, we will. No, it's okay. It's 40 minutes are there. So I'll close this meeting now, and then I'll reopen it around 4:45, 4:50. Okay, participants. Okay. Thank you everyone. Thank you very much. And please come back on time, all participants. Madam, you know, you have experienced, madam, right? On day one. So please come on time. The ma'am will start sharp 5.